Okay, welcome to the last lecture in week 4 of machine learning foundations. In this lecture, we'll state the spectral theorem for the real case, and we'll also apply this theorem to diagonalize a matrix, a simple 2 cross 2 matrix, and in particular, as I've mentioned in the previous lectures also, the main idea, the spectral theorem implies diagonalizability for an important class of matrices, which is the real symmetric matrices. So it says that any real symmetric matrix is diagonalizable. In particular, it's orthogonally diagonalizable. So we'll understand what it means to say a matrix is orthogonally diagonalizable. And we'll just state this as a fact. In the subsequent lectures, we'll prove this fact, this theorem, in a more general case, which is for complex vector space, where the generalization of a real symmetric matrix is what is called as a Hermitian matrix. So we'll prove spectral theorem for a more general case subsequently. But in this particular lecture, we'll just state this for the real case, take an example, and understand how I can orthogonally diagonalize this matrix. Okay, from here on we'll spend a few lectures in arriving at the following main result on diagonalization of real symmetric matrices. So the result is, imagine A is a real symmetric matrix, then the following facts are concerning the matrix A are true. So the first thing is eigenvalues of A are real. The second fact is eigenvectors corresponding to different eigenvalues are linearly independent. And 3, and by far the most important fact, A is orthogonally diagonalizable. This is a twist to the usual diagonalizable claim. What do I mean by orthogonal diagonalizability? This means there exists a matrix Q satisfying such a matrix is an orthogonal matrix such that A can be written as Q lambda Q transpose, which is the same as, I write it like this, x1 until xn, the eigenvalues and Q transpose. So this is x1 transpose, x2 transpose, and so on until xn transpose. Is a real symmetric n cross n matrix. Just a minor fact, this implies Q inverse equals Q transpose. So what we have is A is diagonalizable in the conventional sense, plus add an orthogonal matrix. for diagonalization. This is orthogonally diagonalizable. So this is like saying A equals Q lambda Q inverse, and this is like saying that Q transpose Q equals I, and this just means A is Q lambda Q transpose. So this is the major fact. We have not shown this, but we will show this with some, after covering some background. But this is a fact right now that you can believe. If a matrix is real symmetric, then it is. Now the important thing is, you need a real symmetric matrix. Any real matrix is not diagonalizable, and we have seen an example before in one of the earlier classes. Any real matrix is not real, diagonalizable. Mark 1, let us say 2. Any real matrix is not necessarily diagonalizable, but a real symmetric matrix is diagonalizable. And we can also find an orthogonal matrix to diagonalize it. We already seen this example of a matrix which is not diagonalizable in one of the previous lectures. For example, A is this is not diagonalizable. Yeah. So let's do an example to understand orthogonal diagonalizability. Take the matrix is 1 minus 2 minus 2 minus 2. So pause the lecture video and do the calculations on your own. Just going to give out the main result. If you look at the eigenvalues are lambda 1 equals minus 3, lambda 2 equals 2. The corresponding eigenvectors, I am going to denote them as q1 and q2 simply because I put this in a matrix which is called q1, or let us say x1. x1 is 1, 2 and x2 is minus 2, 1. I am going to make a q1 which is x1 divided by length of x1. This turns out to be, what is the length of x1? 1 square plus 2 square, it is 5 with a square root. 1 by square root 5 into 2, and q2 is x2 divided by length of x2. This turns out to be again 1 by square root 5 minus 2, 1. Now you make up a matrix Q which is just Q1 and Q2, which is 1 by square root 5, 2 by square root 5 minus 2 by square root 5, 1 by square root 5. Then of course you can check this, check Q transpose Q is identity. This is something you need to check. When you are doing your calculation or answering an exam problem, if you have actually found a orthogonal matrix, the sanity check to do is check this. Now, what is Q lambda Q transpose? This is this matrix 1 by square root 5 minus 2 by square root 5, 2 by square root 5 by square root 5. The eigenvalues are minus 3, 0, 0, 2 into this inverse is just the transpose. So, 1 by square root 5, 2 by square root 5, 2 by square root 5 and 1 by square root 5. This, if you check, turns out to be the matrix E, which is 1 minus 2 minus 2 minus 2 to E. So, again check this. Okay. So much for an example. So, the important point is I could diagonalize this. Obviously, I could also diagonalize with these vectors x1 and x2, but if I put x1 and x2 as columns in a matrix, then they won't satisfy this relation, which is Q, orthogonality requirement, which is Q transpose Q equals I. Whereas, when I normalize them and if I put them in a matrix, yes, they will satisfy. So that is the deal. At this point, I will have to cover some background to show this main fact, which is any real symmetric matrix is orthogonally diagonalizable. I need to cover some background on complex matrices. I will do that now and then come back to showing that any real matrix is orthogonally diagonalizable. So, we will cover the background on complex matrices now. Quick summary before we end this lecture. What did we understand in this lecture? We just stated the spectral theorem, which just says that if I have a real symmetric matrix, then I can orthogonally diagonalize it, and the diagonal matrix will contain only real entries which correspond to the eigenvalues of this matrix. These are two important facts that come from spectral theorem. And the important point is we are looking at real symmetric matrices, and spectral theorem says that it's diagonalizable, but any real matrix is not necessarily diagonalizable. So, that's an important thing to understand. But there could be real matrices which are not diagonalizable. We saw an example in this lecture. And the most important thing is we learned by example by taking a 2×2 simple 2×2 matrix, and we orthogonally diagonalize this matrix by calculating the eigenvalues, corresponding eigenvectors, and then normalizing them. So, we got a set of orthonormal eigenvectors, and then we use this orthonormal eigenvectors to make up the eigen decomposition of this matrix, which is effectively saying this matrix is orthogonally diagonalizable. In the subsequent lectures, we will be looking at a more general case where we look at complex matrices, and the generalization of real symmetric matrices would be Hermitian matrices there. We will show that every Hermitian matrix is diagonalizable, and that just implies the spectral theorem for the real symmetric case, because real symmetric cases are simple special cases of a Hermitian matrix.